This video corresponds to contribution, the coexistence of bound states for BOSE-EINSTEIN condensates with attractive and repulsive interaction in square and parabolic wall potentials by Juan Pablo Cordero Santiago in poster session modality. Symposium, Material Science and Quantum Technology. 32nd International Materials Research Congress. When the temperature of a gas of atoms is reduced close to absolute zero, these atoms reduce their kinetic energy, and they occupy the ground state. Therefore, a Bose-Einstein condensate BIC is a gas of atoms that occupy the same quantum state. The corresponding Hamiltonian of the system is given by this equation. We can express the interaction potential between two particles in terms of a Dirac delta function and any constant GGP, call it the nonlinear coupling constant. The interaction between atoms of the BIC is repulsive when the nonlinear coupling constant is positive. On the other hand, the interaction between atoms is attractive when the nonlinear coupling constant is negative. From the Hamiltonian of the system can be derived the Gross-Brzezinski equation, where h bar is the Planck constant, mu Gp is the chemical potential or energy of the system, and phi is the wave function of the BIC. Let's remember that atoms in the BIC occupy the same quantum state. Then they can be described by the same wave function. That is, the condensate behaves like only one big atom, and its associated wave function is solution of the Gross-Brzezinski equation. This equation is also known as time-independent nonlinear Schrödinger equation. This work is focused on the nonlinear Schrödinger equation in one dimension expressed in equation 2. This one is written in oscillator units. Let us now consider the square wall potential given by equation 3. In this case, the nonlinear Schrödinger equation has analytic solutions, even and odd. These are expressed in terms of Jacobi functions and hyperbolic functions. If G is positive, even and odd solutions are given by equations 4 and 5 respectively. If G is negative, even and odd solutions are given by equations 5 and 7 respectively. Here ME, mu, and C are constants, and they are determined by the normalization condition and matching conditions at x equal to R0. Figure 1 shows two pairs of analytic solutions for a square wall potential. To the left, case of a BIC with repulsive interaction between particles. To the right, case of a BIC with repulsive interaction between particles. We use analytic solutions given by equations 4 to 7 for determining bound states and energy values mu, allowed for positive or negative values of G. Figure 2 shows the behavior of energy mu with respect to the size parameter psi, considering two cases. First case corresponds to a fixed positive value of G, and second case corresponds to a fixed negative value of G. Every curve is associated to a quantum state. We can discretize the nonlinear Schrödinger equation in one dimension to obtain the vector value function given by equation 8. The Newton update can be expressed as the sum of kth iteration of phi and a delta vector. The kth delta vector solves the linear system given by the equation 10. Here J represents the Jacobian matrix of the function given by 8. Newton's method requires an initial guess. For more details, see the reference 4. We have implemented the Newton's method to find solutions to the nonlinear Schrödinger equation in one dimension. We use the Newton's method for calculating numerical solutions to the nonlinear Schrödinger equation with a parabolic wall given by equation 11, analogously to the square wall case, Our goal is to determine quantum states and their allowed energies for fixed positive or negative values of G. Figure 3 shows the energy mu as a function of the parameter psi, considering two particular cases. Conclusions. For the square well and the parabolic well, the energy values associated to solutions to nonlinear Schrödinger equations are discrete. In both potentials, the existence of bound states depends on the parameter of size psi and the nonlinear coupling constant G. When G is positive, the threshold of the localization exists at mu equal to 0 for ground and excited states and considering both potentials. That is, the bound state exists only if mu is less than or equal to 0. When G is negative, the threshold of the localization exists at mu less than 0 for ground and excited states and considering both potentials. Moreover, mu as a function of psi has a minimum for some values of G sufficiently large. Thanks for your attention.